Hello everyone! Let's create a simple effect that resembles a waterfall with several layers of animated water. Something like this can be useful in many 2D games, and it won't be too demanding on the GPU. So let's get started. This time, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background, which will be later turned into a transparent one. So I'll create a new scene and set everything up. Right-clicking the Scenes folder, create new scene, and this time it would be user interface. Let's call it Waterfall. Okay. And right-clicking the root node, add child node colorrect. And in the inspector, I'll change the color to the black one, expanding layout, transform, and changing the dimensions, the size to 1920 by 1080, the full HD resolution. Okay. Let's scroll down to the material section, creating a new shader material, click and creating a new shader type, shader mode canvas item, path would be shaders/waterfall.gd shader, create and click again to open it in the shader editor. Okay, and as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function, deleting vertex and deleting light. Control S to save. Okay, this time we don't have an image available from which we could determine the resolution, so instead I'll add a uniform parameter to define it. And as we could see at the beginning of the video, this will be an animated effect, so we'll also add a parameter to define the speed of this animation. Okay, uniform, vec2 resolution, and it starts at our full HD 1920 by 1080. Okay, and the second one, a uniform float speed with a hint range, and let's set the initial speed to 1, and the range would be from 0 to 10 with a step point 0.01. Okay, and we can write the basic version of the fragment function. The effect we are creating will be symmetrical around the center, so I'll start by shifting the origin of the coordinates to the center. And because we are working with UV coordinates, that is in the range from 0 to 1, it's enough to subtract 0.5 from the UV variable. So I'm deleting the comment, and now vec2 UV equals UV minus 0.5. Very well, next we want the effect to look the same regardless of the dimensions of the element, in our case the colorrect. So I'll recalculate the aspect ratio using the usual formula. uv.x is multiplied by resolution x divided by resolution dot y. Let's continue by defining a time variable. As we know from previous tutorials, it will depend on the internal time and the speed parameter. Float time equals time times speed. With that, the basic fragment function should be ready, and we can move on to implementing the helper functions that will make up the entire algorithm. Okay, so first, we'll need a generator of pseudo-random vectors, which we'll use to define the structure of the waterfall's water layers. As you may remember from previous tutorials, I use various types of calculations, and this time I'll use one from a shader that generates dynamic fog, since flowing water has a very similar structure. So I'll insert a function called hash22. And let's put it here right before the fragment function, hash22. Okay, so it takes vector2 as the input parameter and returns vector2 as the return value. Okay, next we'll add a function that defines what's known as simplex noise. This is a type of pseudo-random structure that differs from classic parallel noise in that it uses a triangular grid instead of a square one, which makes it much more suitable a much more suitable texture for an expanding waterfall. I recently used a similar algorithm in a wildfire effect tutorial, where I worked with sawtooth functions producing very similar shapes. Anyway, it probably wouldn't be very useful to explain all aspects of simplex noise in this tutorial. If there is interest, I can create a more detailed video in the future covering different pseudo-noise generators and their differences. For now, to save time, I'll just paste in a ready-made function. But first, let's define two constants that simplex noise is based on, the so-called skew and unskew factors used to transform coordinates into a triangular grid and then back into standard coordinates. Okay, I go back at the uniform parameter section and after them const float s for skew in capital letter, and it is square root of 3 minus 1, and everything is divided by 2. This is the first one, and the second one, const float capital U for unskew is 3 minus square root of 3, and everything is divided by 6. Okay, and for the function itself, I'll simply call it noise, and let's expand this, and insert it right after the hash22 function, and here it goes. Okay, to compute the final noise structure, we'll use something called fractal Brownian motion, FBM, an algorithm I've already described in detail in previous tutorials. You can also find it in an excellent online resource called the Book of Shaders, which I've linked in the video description. In our case, it's a sum of several iterations of simplex noise with different parameters. In each step, we halve the amplitude and rotate the UV coordinates using a rotation matrix that performs two operations at once, a rotation of about 37 degrees and a scaling by a factor of 2. Thanks to this trick, the individual layers will blend smoothly together and will avoid unwanted visual artifacts. So let's write it here after the noise function. Float FBM with a parameter vector 2 UV coordinates of the current pixel. Okay, and now float F is 0. This is supposed to be the return value, so return F would be the last line and now the body. The rotation matrix, as I mentioned, let's call it M, is met2, which consists of two-dimensional vectors, 1.6, 1.2, and the second vector is vec2, negative 1.2, and 1.6. Okay, so this is just a short for what is wrong. Vec, this is not correct. Vec2, yeah, this should be right. Okay, rotation about 37 degrees approximately, and scaling by 2, which gives us these values, which are cosines and sines of the mentioned angle multiplied by 2. Okay, and then there are iterations. Float amp equals 0.5, and now the cycle for float I starts from 0 and number of octaves, and this is something we don't have in our parameters yet, so I'll add it briefly. Let me first write the body of this loop. So f is increased by amplitude times our noise function applied on the UV coordinates. Next, let's transform coordinates, rotate them by the matrix, and scale up. And finally, amplitude is increased by 0.5, so we are halving that. Okay, and now I will scroll up to the uniform parameter section and write the missing parameter, uniform float octaves with a hint range, and I think I started with 5 octaves, and it goes from 1 to, let's say, 10, and the step is, of course, 1. Very well. So this summation gives us a result roughly in the range from negative 0.94 to 0.94. However, we only need positive values, so I'll remap this to an interval that ends up being approximately 0.13 to 1.07, and the transformation is f times 0.5 plus 0.6. Okay, now it's correct. All the preparation is now complete, and we can start improving the fragment function. Falling water usually doesn't have a constant color. It changes depending on the reflected light and generally achieves an organic look. To help with that, we'll prepare a variable that oscillates over time, and I'll define it like this. So going down to the fragment function and the new line float fluctuations equals absolute value of sine of time in lowercase. Okay, the first thing we need is to use the FBM function to prepare the rendering of the waterfall. However, since we'll be repeating this process to create multiple layers, I'll take a small detour and add a function called water layer. Inside it, I'll generate a moving texture for the current pixel at a given speed. So let's go right before the fragment function and write this float water layer with parameters vec2 uv, float time, and float, let's call it power, to define the speed and other aspects of this particular water layer. And now float. Let's define variable float, which is simply power times time and increased by the absolute value of uv.y. Let's remember that our coordinate origin is moved to 0, 0 to the center, so uv.y can be actually a negative number. That's why we use the absolute value, and let's return the FBM function value applied on uv times power and minus vec2 0 and flow. So we are moving only over the y-axis, only vertically. All right, and to control the structure of the water layers, I'll add a new uniform parameter called density. Uniform float density. Okay, this time without a typo, and the hint range and the initial value, let's say 5 again. Okay, and the range should go from 1 to, for instance, 50 with the step 0.01. Okay, and I'll use it for the first layer. I'm scrolling back to the fragment function and writing the next line, float. And for noise is water layer applied on UV, time, and our density. Okay. You might remember, perhaps from the raindrops on glass tutorial, that we usually create multiple layers and sum them together. This time, however, I'll do it a bit differently and add a second layer in a way that produces a much better looking result, like this. So n would be increased by n divided by water layer and parameters UV, time, and this time density multiplied by 5. Okay. Now I can incorporate fluctuations into the algorithm. I'll do it in a way I arrived at through various experiments. So n is multiplied by 4 plus power of our fluctuations to the power of 5. Okay, and the rest let's divide by 10 multiplied by 0.1. Okay, let's move on. To get the waterfall into the desired shape, we need a mask to crop the noise texture. So let's add a parameter to define the width of this cut. Okay, scrolling up to the uniform parameter section, uniform float cut with a with a hint range, and the initial value would be 2, and the range goes from 0.1 to 10 with this usual step 0.01. And now for the shape, I'm going back to the fragment function. And what works quite well here is a function shaped like an elongated ellipse with its bottom cut off, something like a parabola. It will be this line, vec2 elliptical is vec2 with parameters cut parameter plus uv dot y times 1.5, and the second is simply 0.75. Okay, now using this ellipse, I'll define the silhouette of the waterfall based on the distance of individual pixels from the origin, which is at the center. Since uv.y can also take negative values, we'll use the max function to clamp negative values to 0. Float silhouette is max of 0 and length function applied on uv times our elliptical vector minus our noise multiplied by max 0 and uv dot y times plus shift 0.25. Okay, and now for the final mask, I'll subtract it from 1 to get the exact inverse. Pixels outside this shape will be multiplied by 0, while pixels inside will be multiplied by values close to 1. This removes all the surroundings, leaving us with just a moving waterfall. Float mask is 1 minus 10 divided by the absolute value of uv dot y and multiplied by our silhouette. Alright, I know the code so far may not be the easiest to understand. The challenge is that to make the result resemble falling water, the algorithm cannot really be simplified much further. But don't worry, we're getting close to the end and you'll see something soon. So, what were all these calculations for? Now, using the value n, this one, that is the combined moving noise, and the value mask, we can determine the color intensity of the current pixel. We'll also incorporate uv.y into this formula so that the intensity changes with the height of the falling water particle, like this. Float water is n times mask times 1.5 minus uv.y. Okay, now we can finally determine the actual color of this pixel. For that, we need to know the hue of our water as well as its brightness. So I'll add 2 more uniform parameters. Scrolling up, and uniform vec3, the RGB color with a hint source color. As we know, this brings the color picker in the inspector, and the initial value would be vec3, I think 0.5, 1, and 1 for a shade of something bluish, I suppose. Okay, and the second one, uniform float brightness. This time with hint range, and the initial brightness I set to 1.5, and it goes from 0 to 10 with the step 0.01. Okay, and since we want to emphasize the brighter pixels, we'll use the fourth power of the water value. We'll just put it to the power of 2, a power of 4, which I'll then multiply by the color and brightness parameters. So going back to the fragment function, and the next line is vector3, and let's call it RGB for the color in RGB format. And as I said, I put it to the power of 2 water, to the power of 4. I keep saying 2, it's 4 of course, and times color times brightness. Okay, is that correct? Yes. Next, we need to determine the alpha channel value. Since water is at least partially transparent, we'll again use the computed mask, this parameter, this variable I mean, and also vary the transparency with the pixel's height, because a waterfall is usually densest at the top and gradually becomes thinner towards the bottom. So let's define A for alpha. Float A equals mask times 1 minus power of the absolute value of uv dot y, and to the power of 10. Okay. Now when I think about that, I think the absolute value is not necessary, because when we are calculating something to the odd, to the even power, it automatically becomes the positive number, but let's keep it there, it cannot hurt. Just in case we change this argument to some kind of an odd number. Okay, and that's it. We compose the final color by mixing it with a transparent black pixel. So color, the output value, is, as we know, vector4, which consists of the mentioned mix. So our transparent black color is the first argument. Sorry, it's supposed to be vector3, of course. The second one is our RGB color, and the weight value is A. And let's put the transparency to 1. Okay, and we can already see something right here. Let's take a look at the result. All right, but several issues are immediately noticeable. It seems the noise texture still has a certain roughness that we wouldn't expect from water. So let's improve the hash22 function using one last uniform parameter. First I'll add it, so I'm scrolling back to the uniform parameter section and writing the last parameter, uniform float smoothness. With a hint range and the initial smoothness, we can set to 100 to make it really smooth. And it goes from 1 to, let's say, 1000. And the step 0.1 is sufficient. And now I'll use it in the code. Let's find the hash22 function. And instead of sine uv, it would be sine uv divided by the smoothness. Wait for it. Okay, I think the result looks much better. However, the waterfall is still too overexposed, so I'll go back to the calculation of the water value, scrolling down to the fragment function. This is the water value. And we should smooth the transitions between different brightness levels. So I'll add a small adjustment using a sine function, which would be then remapped to the interval from negative 0.5 to 0.5. So water is increased by sine of water times pi and pi and remapping to 0.5 to negative 0.5 to positive 0.5. Okay, and to achieve a more watery color while preserving brighter pixels based on the uv.y coordinate, I'll make one final tweak. Water is multiplied by 0.5, no, 0.9 minus the power function of uv.y to the power of 2. Okay. Yes. Now the water flows nicely, and although it's not a perfect simulation, we can say we've achieved a solid result. If I now play around with the parameters, we can see what can be changed in the final effect. So let's go to the inspector section and expanding the shader parameters. And first, speed. I think it's self-explanatory. If it controls how fast the water falls, so I can make it pretty fast. Yes, or I can put it to the full stop. All right, now it's frozen completely in time. Let's get back to some speed. Octaves, increasing them shouldn't have a huge effect, but lowering them gives something like a tune effect. Does it? Yeah, maybe. Okay, let's go back. Then the density. This can be also quite interesting if we reduce it to a minimum. Let's try it. Yeah, very interesting. And combined with a low octaves value. Now this is something completely different. Let's revert. How does the cut work? Increasing it gives us a very narrow stream of water, while decreasing it produces something like Niagara Falls. Very nice. Let's go back. As for the color, it's obvious too. If you want a green radioactive slime, let's set this parameter. And again, I'll decrease octaves and density. So we get something very slimy, which could resemble something very dangerous in our game. Let's get back. Okay, as for brightness, it's also straightforward. What's interesting is that in lower values, we can still see something like the white sparks, or maybe not. I think I might have some typo in the code, but I'll get to that later. Okay, and last thing. Just like with other effects, it would be very useful here to display the waterfall on a transparent background, so we can easily add it to the game scene later. This time, thanks to an already existing variable a, this one, we've saved a lot of effort. We just need to replace the value 1 right here with a. If I do that, wait for it, and this is the perfect result. Okay, but of course, if you want to preserve the black background, let's just revert to the original one, and we are back. Okay, and I found the typo. It's right here in the water variable definition. I got 1.05 here. It should be just 1.5. Let's fix that. And now it's definitely a better mix of white pixels and the water pixels. And if I change the brightness again, lowering, we can see, yeah, that's exactly what I wanted to show before. The water is darker, but the white pixels are still very prominent, which gives us a very interesting result. Okay, let's get back. And this is definitely everything I wanted to show this time. Thank you very much for watching, and I hope you'll find this effect useful. There are plenty of possible applications, whether as a background decoration in a 2D game or as an obstacle the player must overcome. And just like with the wildfire effect, the entire algorithm is computationally inexpensive, so it shouldn't significantly impact game performance. And as always, I'll also add this shader to the Godot shader pack, which I've linked in the video description. For now, take care, good luck with your projects, and I'll see you in the next video.